Good afternoon and welcome to our series on talks for a general geoscience audience. As you know, the theme of this conference is a voyage through scales, and we have two dedicated talks on the theme for a broader audience. We had one talk yesterday, and today's talk is on the Continental Crust, scales and the Continental Crust, and I'm particularly pleased to welcome Professor Chris Hawkesworth to give the talk today. I'm glad you are coming. Chris, the stage is yours.
Thank you very much, Gunther, and thank you all for coming in over lunchtime on this wonderful day. We heard yesterday, I think usefully, how in the subject of water and terrestrial systems, there's a clear scaling up process all the way through from studies of pores and water and mineral surface interaction up to making regional models. Let me make the case to you that perhaps the notion of scale raises rather different questions in geology. And let me start with two asides, I think. The one is, in this change of scale, I can still remember as a graduate student sitting in my supervisor's office, drawing nice pictures of plate tectonics in the Alps and flake tectonics, and now you know who he was. And then going out in the field and being faced with this awful little outcrop of rock, right? I mean, the jump from those nice simple models that we devise sitting at our desk and thinking about large-scale processes to the rock record is considerable. And I think it's one that students struggle with and we learn to adapt to, and I think it's a key part. So one of the things I'll emphasize particularly today is the link from outcrop to bigger scale models. And the other is the issue of the nature of that record. I mean, I'm sure we've all been in the field with students looking at early outcrops, they haven't seen very many, and really getting frustrated that they couldn't see anything in this outcrop. And usually they're right. Actually, you have to move around the geological exposure, all right, to find a place where you may be able to say something. So if this wall was a rock surface and there were 3 or 4 places where you might find an unambiguous answer, our relationship to the record and our relationship to interrogating the record may be different from the kind of things we heard about yesterday. So let me illustrate this initially with a slide of geology in the Damara. The Damara is a Pan-African orogenic belt in southwest Africa, in Namibia. And here is a slide of granite, basically granitic magma forming in situ, melting high-grade granulite facies metasediments. And clearly in the field you can see cross-cutting relationships, you can see how those things work. You can also date this material. We're increasingly good at taking zircons, at looking at how complicated they are, at analyzing spots within the zircon so we're confident of what we're analyzing, and getting ages that we think we understand. But going from this kind of discussion about exactly what happened here to this is the big step that's tricky for us all to grapple with and to find ways to do that. And even if we've established that the Damara is, let's say, a collision environment 550 million years ago, it's another big step to say, well, how does this relate, first of all, to the other orogenic belts in Africa? And thirdly, how does it relate to the evolution of the Earth? Are these orogenic belts that are in some way particular to this time in the history of the Earth, or are they not? And there is a big issue about when I study my orogenic belt. Do I know it's typical of the Earth at that time? And that issue about regional to global, I think, is there throughout these discussions. So here then is a sort of summary of the things we might think about and touch on. The links between different scales is clearly why we're here. This just shows you a thin section to hand specimen to outcrop in the Damara to regional fold structures within the Damara as a geological context. We've got very good at analyzing smaller and smaller material ever more precisely. So we have, and the key point about that is not only nice precise zircon ages, but we have much more confidence in what we're analyzing. We can image it, we can identify it, and we have much more sense of what's being hit by our ion probe or our laser beam. But all this data produces questions over data handling. Most obviously, maybe initially, iron probe data. Huge numbers of data generated on a few spots, and statistically addressed on the basis that those spots are all dating the same age material. But if you're looking for subtle differences in age within a zircon, it's very hard to know how best to treat the data. So there are huge data handling issues that we're getting better at, perhaps. We've known since Charles Lyell that the geological record is incomplete. Now, the stuff we've lost, was that representative? Or did we lose some rocks more than others? Turn it round. Is the stuff that's left representative? Or have we hung on to some rocks more than we've hung on to others? So as soon as we admit the record's incomplete, does that mean it's biased? And what can we say about that? And this is clearly about this issue of changing scale from the outcrop level through to developing models. And the bottom one is the one that I've touched on already, and that is how do we address, and I think we're not very good at it, the significance of the regional event we've just done, particularly back in the Archaean where there's not much rock. If I demonstrate a subduction zone in Greenland, does that mean there was subduction everywhere on Earth? These are tricky issues to nail, but they're fun. That's why we're here. All right, let me start with zircons. Up in the top is just a classic picture of a complicated zircon that has an igneous core. You may not be able to read, it doesn't matter, 130 million years. It has igneous material at 96 million years, and it has metamorphic zircon on the outside at 6 million years. But we can do that now. We can image it. We can hit spots. We can date different parts. And let me make a slightly sweeping statement. I think in lots of these studies, we are drawing on other sciences, all right, in mineralogy and crystallography, in structures of minerals. And the bit that is perhaps different from the other sciences is as we go to bigger scales. Then the other issue is, with greater confidence what's being analyzed, is it's increasingly clear that many whole rocks we thought were nice representative whole rocks are actually made up of a mixture of minerals, of different history, for want of a better word. And this is a whole rock sample from the Lachlan Fold Belt in southeast Australia, and this just illustrates the point. So this is hafnium isotopes in zircon and neodymium isotopes in the whole rock. So there are 5 whole rocks, and for those not familiar with the diagram, anything positive on these diagrams is sort of mantle, and anything negative is crustal. So this would be a mantle component. So what's really amazing is you take one whole rock sample, and you take the zircons out of it, and they show a range in compositions of 8 epsilon units. The units don't matter much, but they're not homogeneous, all right? So they have had crystallized from magmas of different isotope ratio and become mixed together to give you this whole rock you're trying to interpret. The good news is, of course, is you can analyze the minerals and separate out what those mixing processes might be. But if you thought the whole rock was a simple representative lump of magma that was behaving simply, then that's clearly not the case. I mean, the interesting news here is that these are sort of mantle end member rocks, but they've obviously got quite a lot of crustal material in the Zircon record. And these were granites that were thought to be melt of sediments in the crust, but actually they've got a bit of mantle in them. Thermally, that's a help. It's much easier to melt your sediments if you put in some heat from the mantle with some basalt. But if you didn't have these zircons and this range in single whole rock compositions, it would be hard to unpick. I just had to put the slide in, really. Cathedral of your dreams, time-wise. Inside a zircon, all right? Authors are down here on the right. Nasdala et al. It is a wonderful image. The bad news is, of course, right, is that the sense of being a cathedral is developed because of all those nasty cracks, which meant that you wouldn't be able to get a good date out of it anyway. All right? So really, the structure of the zircon here, these are the zircon growth zones, and these are cracks that crack through it and break it all up, and would warn you perhaps not to analyze that zircon. So we're used to analyzing zircon. It's what's given us our best data on the timescales of Earth evolution. It crystallizes from granitic high silica rocks, and it's hard to destroy, so the story goes. And what is a nice touch in a way, many of us use the decay scheme lutetium to hafnium to look at Earth evolution processes. We often analyze hafnium isotopes in zircon, And actually, zircon was the mineral from which the element hafnium was first isolated in the 20s in Copenhagen. And as I recall, hafnium comes from the Latin name for Copenhagen. So that just brings that full cycle. Let's move then from minerals into the rock record. So this then is a summary of marine in blue and terrestrial sediments from the Cambrian to the Neogene in Spain, France, England, and Wales. And it's simply to highlight that, as we know, things are cyclical in the Earth. Now, these people were interested in finding fossils, all right? And clearly what this highlights is, if you're looking for a marine fossil wandering this part of Europe for rocks in the Permian, you'd be hard pushed. If you wanted a terrestrial fossil, Ordovician's not great. So this gives you a sense immediately about the record not being complete. And there's perfectly good reason for it. Presumably these are times of high relief and lots of erosion, lots of terrestrial sediment, and the same over here. And in between, you've lots of marine sediment. So it's not that it's odd, it's just the nature of the record that is cyclical, seen here in sediments, particularly in this case, driven by people looking for fossils and how they could find better ones. And the same, of course, is true of orogenic systems. Now, we've known this for a very long time. The Irish of us here had to use John Joly in the 1930s, who was a professor in Trinity College Dublin. This is, the Alps as they are now, all right, as an active mountain belt. And my history geologically as a student was to work in the Alps and then go to the Pan-African. So here's a map of southern Africa. The Pan-African is this mobile belt here in white. This mobile belt, which was a mountain series, is now flattened by this tertiary peneplain. And while it's wonderful you have 100% rock exposure, all those nice fossils and blue schists and things and sediments that make it easy to interpret the geology of the Alps have all gone. You've eroded, 10 or 15 kilometers through the Alps, and this is what you're left with. You're left with that in situ melting to make granite and give you uranium ores in the center of the Damara belt. So clearly, again, the record's not perfect, and doing this to this, does it bias the record in what we're left with? And this then is really at the core of many of the recent debates. And this is a plot of, again, hafnium isotopes. Remember, it doesn't matter much, but above zero is sort of mantle-like, and below zero is crustal-like, plotted against the crystallization age of the zircons. There are hundreds of thousands of zircon analyses. People date them for every rock. They want to know the answer about age from, if it's of the right composition. And all I want you to look at really is that if you look at this axis, there's a continuum of hafnium isotope ratios if you look across the whole diagram. There's no real breaks going this way. But what remains striking is that if you look at the crystallization ages, there are clusters of ages, and there are times when there don't seem to be very many ages. Now, these are zircons, but you can think of them as granite, all right? So there are times when there was lots of granite generated. This is globally. There are times when there wasn't much granite generated, according to this data set, globally. Is that likely in a steady-state Earth doing plate tectonics? So this is, if you like, the shift from the regional orogenic systems of the Alps, of the Himalayas, of the Damara, to some kind of global database that still says there are times of lots of magma and times with much less magma. These may well be some kind of cycle through time. They're there for us to interpret. You can see the same kind of distribution if you look at this as amounts of gold against age. And there's long been a discussion about whether the Archaeans are a particularly good place for generating gold deposits. There's some here in the Proterozoic and lots more recently. What is the age? What is the control, in essence, on the ages of these samples and how we take them forward? And then on a regional study by Campbell and Allen, just highlighted the point that again you get, which is exactly the same as those purple dots, these peaks of ages and troughs of ages, peaks of ages, troughs of ages through the geological record. Remember, these are peaks of making granite magma. troughs of making granite magma, peaks of making granite magma. And what's interesting about them is that they coincide, the peaks do, with the ages of supercontinents in those grayish bars. Now, supercontinents are not always agreed on as to how robustly they're recognized, but if we take them as red, then it's interesting that these peaks match up with the ages of supercontinents. And if you think up here in plate tectonic terms, in essence, we have plate tectonics going on, we have ocean crust being generated and it being subducted. A lot of subduction goes on before you move these continental masses together to make a supercontinent. Huge amounts of magma are generated, as in the Andes and places, as this stuff goes down, as you close the oceans before you make a collision to make a supercontinent. So how come all this magmatism, all these granitic rocks that might have been generated during subduction, is not displayed here? What's displayed here is the granites at the collision time, not the granites so much in between. And you can do one other study, which is from Mike Brown, and this I want to isolate a particular point. So this is the Zircon age peaks in the background, the supercontinent ages in the background, and Mike Brown highlighted that if you plot against thermal gradient, all right, for granulite facies and high-pressure rocks, yeah, then these are them in orange, in green, and in blue. And there are 2 points. Clearly, you can do changes through time, all right? The blue, very high-pressure rocks, low thermal gradients, appear to be restricted to the last 600 million years of Earth history and might reflect the onset of plate tectonics. All the others are continuous across the piece. So this temporal relationship of this arriving is fine. What is really much more difficult to understand is why the granulites cluster in ages with the other zircon peaks, and whether we really believe these are primary signals of making granulite at this time, but not at that time. So there's the quandary. If people make peaks of magma, then they most often appeal to some kind of plume activity, yet we're faced with a steady state world where lots of subduction's going on, and globally we should be generating similar amounts of magma through time. The difficulty with making those apparent peaks by plumes is that all the data on the chemistry of the crust is dominated by subduction zones. So what we were interested in then, and so have others been, is what not only are the volumes of magma generated, but the volumes of magma destroyed compare. And if we think about the Andes, as we've just said, as you're subducting, as you're closing this ocean and subducting huge amounts of material, you're generating huge volumes of granitic and high silica magmas. But what a number of studies have shown is that although you may generate a figure of 3 kilometer cube of magma per year along these kind of margins, you're actually subducting rock at a similar rate. So subduction zones as a place to make long-lasting crust seems to be slightly hard work. You're making lots of crust, but you're destroying it as fast as you make it. In contrast, if you go to the collision zones like the Himalayas, you not only trap in the last phases of subduction in the Karakoram, you also trap in the high silica magmas that have been generated since. So it seemed to us to be sensible, and it seemed to others to be sensible, that if you then think about what happens through a supercontinent cycle, so you have this subduction phase making huge volumes of magma, a collision phase, and a breakup. If you think of magma volumes, they're clearly huge in the subduction phase. As you have collision, you get the last bits of subduction, you get a bit of collision magma, and you get breakup. But if you add on here the preservation potential, the chances of those magmas surviving, in advancing arcs, almost everything gets destroyed. It gets subducted, it gets taken back down again. But as you go into the collision phase, clearly your chances of preservation get ever greater. And if you go to breakup, there's probably not much zircon made anyway, so it's not clear what you'd preserve. So the development of an age peak in here is presumably then linked to the interaction between making lots of magma at a time when it will be preserved, i.e. in the collision zone. And that in our cartoon model is how that looks. All right? So that is a way of explaining why the peak of zircons is not at the time of subduction, but it's at the time of collision, because collision is time when you trap most of the magma that you've generated, and you trap the last stages of subduction. And you can do it one more way, and this is simply to make the same point, that if you actually try and calculate the volume of zircon generated per year in your magmas of various compositions at various zirconium contents of various sizes of zircon, clearly this highlights when you have large volumes of magma, you're going to make huge amounts of zircon. And as you go through to less volumes, you'll get less and less zircon. But your age peak is not here at subduction, it's here at collision. So the wider implication then of this has to be, all right, that we have these age peaks, we have magmas trapped at the time of supercontinents. When we make these collision phases is when we trap most of these granitic records in the crust. And if you pause about that, that means that collision times become the time when the volume of crust increases, not because you've made more crust, but because more of the crust you've made, you've kept in the crust. All right? So it isn't that the mantle has suddenly said, let's make lots more crust at this time. It's just that if you make crust at a steady state, once you have collision, you have more chance of keeping it. All right, and that just summarizes what I've said. So if you look at this thing again, we would say there's a bias set up by the development of supercontinents in the geological record since 3 billion years or so, which many people would say is the onset of subduction. If you go back into earlier times, there are fair numbers of zircons. But the record is small. I mean, the area of Archaean rocks is small. And it's very hard to unpick any sense of bias back here. But if there wasn't plate tectonics, as in many models, you wouldn't expect it to be a bias of this kind in any case. But it leaves us with the question, which is hard to answer, that if you go mapping in Scotland, let's say, how representative are those rocks of the processes that were active in the evolution of the Earth at those different times? And again, this is another, I think, therefore, take-home point. If we plot all these compositional variations through time, how robust are they? Here's hafnium isotopes and silicates, or in zircons, or in most cases. Now, if that record is dominated by collision, and collisions are dominated by a bit more crustal melting than if you don't have collision, then clearly this curve must be lower, it must be more crustal in its signature than what really happened. So we need to be wary about how we handle that. If we look at things like gold deposits or granulites, and granulites are a good example, you can see some temporal change, but the implication of a preservation collision-based model is that the age peaks of those distributions are the things to be wary of as not being primary features. But if you think of strontium in carbonates, that may be fine. You don't need huge volumes of limestone at every time in Earth history in order to get a reliable signal. All right, because you have a well-mixed ocean that's serving you good material. In the same sense, you might make the case about studies on redox conditions in the mantle. Is there any reason they should be biased if the record is biased by some tectonic regime and not others? So I think it's just a question of flagging that it's useful to think of the risks behind some of these records. All right, in the last little bit, then, what I want to do is look at how we go from these regional issues, all right, where we've looked at age profiles, we've taken individual orogenic belts, which we think we understand how they form, we've looked at age distributions, worried about whether preservation has made them different from the primary record. How then do we get back to this long-standing question of when and how the continental crust was formed? This is the present-day volume at 100%. This is from 4 billion years through to the present day. I mean, these are debates that have long been questioned in geology, but in truth have only been addressed since we've had radiogenic isotopes we could usefully use. And what's striking here is if you just take the ages of rocks, we can negotiate what that meant, but if you just look at the ages of different terrains, this is the rock record at the present day. All right, only 7% of the geological record is older than Archaean, and most of these are relatively young ages, which have presumably, in many cases, been reset by younger orogenic events. This then is Allegan-Russo, which is basically looking at neodymium isotopes in shales and is trying to say when the source of those shales were generated from the mantle. And that sounds fine. We can get model ages for shales, we can make that case, and we can see how that would work. And that gives you that nice green curve. What's interesting is that there are curves above that, however they got there. And one of the big questions is how you sample the composition of the crust, and if you do it through sediment, whether sediment gives you a fair measure of the age profile of the crust. If sediments, for the sake of argument, underrepresent Archaean rocks in their sources, clearly the sediment might plot here, but the sources might plot here. So it's trying to move away from the bias of the record in terms of age distributions to the bias you get by how you sample the record as well. And this is a common procedure, widely used, using sediments as archives of crustal compositions. Lots of average crustal compositions have been generated that way, and for immobile elements, it works very well. What's really tricky is if you have age data in your sediment you're trying to unpick. So here's the damera again. Here's the granite and gneiss of the eroded damera. Here's what geochemists might call molasse sequence on top. And if you want to know the composition of the crust involved in this orogenic belt, you take the sediments and you try and unpick the composition of the rocks now eroded. It's worked well for lots of elements. But it means that we need to understand how the proportions of the rocks of different ages that are here compare with those that you get from the sediments that you sample and measure them. And here's just one study from a small river belt in southwest Australia, published a few years ago. Here's the river, here's southwest Australia, here's the river, it's 300 kilometers long, it is not long. But it has the great advantage, it flows from Archaean terrain in pink, down through a mobile belt, the Albany-Fraser zone in green. So you know the sources available to the sediments. And then these are just the sites of different sediments taken for sampling. The graph then shows the relative proportion of Yilgarn, i.e. Archaean, plotted against distance from the coast of the river. So this is the start of the river. Here's the topography of the river with topographic inflection as you come down towards the sea. If you simply go to the map, all right, and do for each sediment, how much of its source area is Archaean? Clearly in the pink area, it's all Archaean. As you come down towards the river mouth, and you take this sample here, 65% of its source is Archaean on the map, just mapped out. But if you analyze uranium-laden zircons, hafnium isotopes in zircons, neodymium isotopes in clays, in those sediments, you get this gray band through these different sediment localities. And when you get to the river mouth, that sediment and the data and the heavy minerals in that sediment only think that 12% of its source was Archaean. So if you're sampling, right, how much Archaean is in this river territory, and you picked up a sediment at the river mouth and you said 12%, you'd be fairly wrong. There are lots of good geological reasons for that, all right, and we can come back to them. So it's not a surprise, and there's a relief in here too, so it's not surprising it gets more and more eroded down in here. Formerly, Allegan-Russo made that into a K-factor, an erosion factor, which is the percent of the mobile belt over the Archaean in the sediment over the percent of the mobile belt over the Archaean as off a map. All right? And shifting from a 65% that was available to this sediment to the 12% that it had in terms of percent of Yilgarn is a K-factor of 15 or 17. But this is a way of moving from those curves which had relatively little crust in the Archaean to implying there may have been quite a lot. And if we just put those K values, all right, into the kind of plot we've seen before, 100% crust, 4 billion years to the present day, here's an neodymium in shales. But if we actually say that K is 15 from that last plot, there was 70% of the continental crust had already been formed by 3 billion years in volume. Is that a surprise? Let's just touch on, then, this issue about erosion and high relief. I mean, we've known for a long time, this is here now in the 1970s, very good correlation between the amount of stuff eroded and mean relief. These are huge reliefs for most of us, but anyway, most of us down in here, most of the systems we're looking at. But if you thought that a relatively small part of the continental crust was orogenic with high relief, you could make the average sediment contribution to the oceans just from those areas of high relief. You'd never sample the rest of the crust. And future generations would go around, sample those sediments in the oceans and say, hey, it was all very young. So that's the bit we're trying to get over. And we can look at it two ways. Here's a map that simply summarizes pre-1 billion-year-old cratons in pink. 500 to 1,000 million-year-old mountain areas in green. And then orogenic areas that are younger than 500 in that hashed line. And what's striking is that even over 500 million years, the amount of pink stuff that got involved in an orogenic system since 500 million years is extremely small. All right? So clearly, if relief dominates the sediments, the old pink ones are going to be underrepresented. And here's something we did at St. Andrews with a student and with Ruth Robinson, who's in the audience. And this is simply taking the present-day neodymium isotope ratios and plotting them against relief for a global database. Those not used to neodymium isotopes, here are model ages down the right-hand side. And what this basically says is if you have isotope ratios down in here, their source rock was about 4 billion years, in here about 3 billion years, here about 2 billion years, and here about 1 billion years. And if you simply take, all right, the mean of all the data with a relief greater than 100 meters, you get a model age of 1 billion years. And yet there are a number of arguments that says everyone thinks the model age of the continental crust is 2 billion years. So the fact that orogenic areas of relatively high relief seem much better at remobilizing relatively young crust than old crust means this bias is always going to be there if we sample the crust through sediments. And I think we were taught it at school. It is interesting that the continental crust evolves with Archaean cores and mobile belts build out from it in the cliched, almost cartoon sense. And now that's mostly true, and our orogenesis happens on the edges. It never gets its hands on the Archaean stuff locked in the middle. So it's bound to underrepresent. So we've come back then to a model, all right, the same thing, volume continental crust, through time with 60 or 70% generated by 3 billion years for the arguments we've just been through. And that gives you growth rates here which are relatively high and growth rates here that are relatively low. And for reasons that we can go into another time, maybe, there are a number of arguments that says this growth rate is low because subduction was taking place and you're putting material back in the mantle as nearly as fast as you're making it. And before that, maybe that predates subduction, and that was much more when we had if you can have intraplate volcanism before you had plates, you would make bimodal silica associations. So let me look then briefly at the Archaean. This is literally a slide on it. One of the key striking things about the Archaean is that you either get black or white rocks in ways that, you can pick up on databases in the Western Australia. If you're in the Andes, this would be a continuum. So these bimodal silica distributions are seen in geologically recent times. I mean, they're seen in flood basalts. They're seen in Iceland. So if you make lots of mafic magma, and when it gets thick enough or hot enough, it remelts to give you high silica magma, you get these bimodal silica compositions. And even those who enjoy hafnium isotopes through time, this too is a bimodal silica plot, because these lines of evolution of the source regions are effectively down the lines of what basalt would evolve along. And each zircon, each dot, is a high silica magma, all right? So the slopes of the lines are the mafic part, and the dots are the high silica part. And again, there's a whole series of arguments that say to make bimodal silica compositions, what we tend to do is make lots of mafic material, put it in conditions where it remelts, and then remelt to make the high silica end. And let me then end with one thing which I hope will try and address this issue of regional versus global studies. Because in truth, I think all that actually happens now is that we get more and more global data together and say, maybe this has more chance of being global than a regional study. And there may well be in the future we can do better than that. What we've been looking at is the geological record of granites and sediments and metamorphic rocks on the surface of the Earth. But mostly they've come from somewhere else. If we could get at the composition of the stuff recently derived from the mantle, i.e. the stuff that's new continental crust, maybe we'd have a chance of constraining the processes better. And one of the things that's intrigued us then is if you take rubidium-strontium ratio against silica in a huge database of recent rocks, rubidium-strontium ratio correlates pretty well with silica. Not a surprise to anybody, but I think it does. And the advantage of using isotopes, all right, if you use strontium isotopes, so this is present day here, 4 billion years over here, evolving this way. Here's the mantle evolving. If you have a crystallization of magmas here, if they have a high initial strontium ratio, and then this is their model age from hafnium or neodymium, the time that their source has been available is between this point and this. And therefore, you can calculate the rubidium-strontium ratio that's required to go from here to here by the time you melt to make the granite. The same down here, if you have an initial ratio of this, and the crustal source was made here, the model age, you can calculate the rubidium-strontium ratio. So you have a chance, if you can get the model age and the initial strontium age, or even better, the initial lead isotope age, to work out the composition of the sources from which the rocks we dominantly sample were made of. All the zircons we get, effectively, in this model, are by definition of the rocks that were generated here, and we're trying to get back to their source rocks. So that's what we did, and Bruno Dweem led on this. And if you take 13,000 analyses out of this global database and put them all together, this is what you get. So this is new crust formation age. So this is the model age from 4.5 billion years to the present day. And this is that time-integrated source rubidium-strontium ratio. Clearly, there's all sorts of statistics in here. Here's the sort of maximum probability line. Here's the 68% confidence limits. And clearly, these lines get tighter as you get towards the present day. It's amazing it works as well as it does. I mean, here it implies that back before 3 billion years, the probability is that most of the magmas that made new crust and were then remelted to give you the magmas that gave you the zircons had low rubidium-strontium ratios. They had silica values in the range of 48%, roughly where your greenstone magmas plot. And then since 3 billion years, that RBSR ratio of new crust, of the sources of the magmas we normally sample, has increased up to a maximum of about 0.09 to a silica values of 57% or so. And then from reasons we could endlessly debate, it decreases to the present day, or towards the present day. Whatever the interpretation, it seems to me very striking that the argument that processes then are the same as processes since is very hard to maintain. And we, in a model that I've already touched on, really have said this is our bimodal silica time, make lots of mafic magma, remelted to make high silica magmas. Then that new crust becomes more and more differentiated with time, perhaps linked to subduction. Those are the data as they are. If you really want to end with a speculation, what's also striking in Central and South America is that rubidium-strontium ratios of magma generated at the present day correlate with crustal thickness. RBSR as a proxy for silica is great. Is it also a proxy for crustal thickness? Might it be? Just in case it is, here then is a plot of from 4.5 to the present day. Here is that melt crust, there's the new crust thickness as inferred from rubidium-strontium ratios versus thickness, increasing from 20 kilometers or so up to 40 kilometers by 1.5 billion years. That's all right, that's fine. But what's striking to me about it is that it basically increases with thickness here at the same time that strontium in seawater is also increasing. And you could make a link between thickening the continental crust since 3 billion years as one of the drivers for the strontium isotope ratio in seawater increasing at the same time. Anyway, so therefore, in summary, gosh, it was 19 seconds to go. Let me see if I've persuaded you that the geological record is not complete, that the kind of rocks we get preserved, all right, depends on where they're generated. And there's very different preservation potential in rocks of different settings. The record is also biased by erosion, all right, in your sampling of it, and by the formation of supercontinents which hang on to more rocks than you otherwise get. So this is geological cycles on a more global scale, rather than the orogenic cycles we're more used to on a regional scale. The implication is that 70% of the continental crust might be there by the late Archaean, and we might get onset of plate tectonics by 3 billion years. And in the context of what we've been talking about, perhaps if we unpick it a bit, geology more than most uses different approaches at different scales. I mean, as we understand the crystallography and the mineralogy of zircon, to be sure about our ages, we may be leaning towards what other subjects do. As we tangle with the nature of the record, as we tangle with how representative it is, as we tangle with how to put regional studies in a global context, maybe those are issues that are more particular to us ourselves. Analyzing smaller and smaller samples, that gives us much greater confidence what we're analyzing. It has led to lots of talk about reductionism straying over from physics and chemistry, but I think those have been rebuffed. This is the geological record is imperfect from Lyell. I think, and I hope I persuade some of you, that there's a bias in what is preserved in the first place. And if you do your sampling through sediments, you introduce a bias by doing that as well. But those are biases that you can address, all right, and biases that we need to see how to take forward together. And the bit that is much tougher is how does my regional study of a particular orogenic belt in the Archaean relate to dominant processes at that time. Thanks very much.
Thank you very much, Chris, for taking us through space and time scales. I must say I enjoyed the talk immensely. Are there any questions or comments on the subject? Yes, could you use the microphone perhaps?
Hi, Chris.
Hi.
I enjoyed that. Thank you very much. So we've been analysing hafnium and zircons from the Himalayas.
Yeah.
Okay, we've only looked at granites from one small country in the Himalayas, but it's all crustal signature. All the hafnium is very negative.
Yeah. Mm-hmm.
So I was just wondering how representative that is of continental collisions back through time. Like you've obviously been through these databases of hafnium and zircon. And, so is that normal, that all the granite in the Himalayas is just continental? So you're not creating new crust in the Himalayas, basically?
So what's the age range?
This is 34 to about 13.
Yeah, okay. I mean, at that stage, I guess I'm not surprised, all right? But I think what the Himalayas has also done is trapped us the Karakoram et al., all right? Okay, so, because if you turn it around, if the only record you had was of crustal melting, you might never get your subduction signal that we all believe in. So it seems critical that the collision phases have to trap, I don't know how many million years, but the late stage of subduction as well. And those volumes may dominate over the volumes of leucogranite. Yeah? But I'm not surprised, but it may just add grist to the mill that the average hafnium crustal curve is lower than it should be.
Yeah, that makes sense. Cool, thanks.
Okay.
Okay, thank you. Other questions? Perhaps I may ask you a more general question. If your government gave you a lot of money, I mean, you know this kind of questions. If you had to decide a grant scheme for furthering these issues globally, how would you go about? What would your main project idea?
Well, I mean, the projects that we are thinking about at the moment are twofold. One is the issue about the initial strontium isotope ratio and the initial lead isotope ratio of magmas at the time the zircon crystallized is available in the silicate inclusions inside the zircon. But that's analytically very demanding. But if you could get that, you would do much better than 13,000 messy hole rocks to understand the composition of the sources of the magma that gave you the zircon. So that would be one. And the other would be much better understanding of what the distributional mineralization is. All right, so how we put this notion that you get lots of rock preserved in the Archaean for whatever reason, when at the end of the Archaean, you get less rock later, you get less magma later on. And this issue then about what controls mineralization through time, and whether we can see that through these biases, would be where I would go.
Okay, thanks. Any other questions? If not, let us thank Chris again for this fantastic talk and enjoy your conference. Thank you.